Alright, so here we are tasked to determine the most acidic proton of the four marked hydrogens. When we first look at this problem, the easiest way to approach it is going to be considering the conjugate bases of all the protons once they've been expelled as an acid. And the reason why that is that the weaker base is going to be the stronger acid. So the most acidic proton is going to have the most stable, the weakest base. When we look at this problem, we're first going to eliminate both of the hydrogens that are attached to methyl groups. And this is because actually of both of these carbons, they're going to produce first-degree carbocations, which are extremely unstable. So it's very unlikely that either of these hydrogens are going to be released as acidic protons. And although the molecule could undergo some hydride rearrangement, it's just very unlikely to occur, especially considering the other two choices that we have over here. So first, let's look at the hydrogen that's attached to the the alkene, the double bond between two carbons. If this hydrogen is expelled as an acid, you might be tricked into saying that the carbanion would participate in the resonance structure that's here, because we have this conjugated system, which is ideal for stabilizing a negative charge. It provides stability. Resonance stabilized molecules are extremely stable. However, you need to look a little bit closer, because recall in molecular orbital theory that if this carbon has its p orbital already occupied with a double bond, then this bond, it's actually going to be going outwards. It's not going to be able to participate in this conjugated system. We can kind of visualize that here. This carbon is an sp2, so let's mark that down. We have sp2 hybridization. If we draw the structure, we have this trigonal planar structure here with both the three sigma bonds going outwards. This is to the hydrogen. And then we have the p orbital, which is above and below the carbon, connecting to another carbon. If we were to remove this hydrogen, then instead we're going to have the electrons of the lone pair of the carbanion sticking out here. We can kind of visualize that. It's a little bit hard to visualize in just this 2D space, but we kind of have them sticking out this way. To participate in the conjugated structure, they'd have to be in line here, going away. So we can clearly see that the electrons in this sigma bond with the hydrogen are not going to be able to participate in the conjugated system. So it's not going to be as stable as you think it would be. In fact, it would just be as if we had a second-degree carbanion right here. You could even argue that it'd be even more unstable because the double bond here is a very electron-rich group already. So this is not a very favorable position to be in for an atom. So let's go ahead and take a look at the last option, because it's entirely possible that that might be the option, but let's just see where we are with the rest of them. I accidentally erasing the problem there. If we consider this hydroxyl group, normally it's taught that alcohols aren't the most acidic. There are more acidic groups because alcohols aren't very stabilized. However, having a negative charge on an oxygen is far better than having a carbocation, especially a first-degree carbocation, or a carbanion, regardless if it's a second-degree carbanion, because oxygen is more electronegative. That's just a simple high school level chemistry question. If we have a carbanion versus an oxygen with a negative charge, oxygen with negative charge is going to be more stable every time. It's more electronegative, can hold the electrons better. Now let's consider, if we go ahead and remove this hydrogen, we're just going to have a negative charge left on this oxygen. Compared to a carbanion, which we saw here, and compared to the first-degree carbocations, which we know are definitely not the most stable, we're going to choose this every single time. Heck, you might even say that this this wouldn't be alpha, but this would be the first hydrogen here, might even be removed so that the molecule can form a ketone group here. But all you have to know is that this, having a negative charge on an oxygen, is going to be infinitely more stable than having a carbanion with an alkene group right here. So, if we're going to choose which proton is going to be the most acidic, it's going to be the proton that was resting attached to this hydroxyl group right here. Kind of tricky, because normally we don't see hydroxyl groups as being the most acidic, unless they have, some resonance structure or, electron withdrawing group. But in this situation, this hydroxyl group is going to be the most acidic out of the other three hydrogens that we listed here. Hope you guys had fun enjoying that small little quick question. It's always good to consider what factors are involved with the atoms, because especially right here, that hybridization question can really trip you up. But as a general rule of thumb, it's pretty safe to consider that the methyl groups aren't going to be the right answer.